This is Dr. Carroll, and this video is going to talk about linked lists. Okay, so what's the context of linked lists? For linked lists, we have, to back up just a little bit to put it in context, we have an abstract data type, ADT, list, and we have a couple options what we're going to do for our implementation. We could have an array-based list where it's contiguous block of memory with multiple objects of the same type. But it also has a restriction that it is a set size, and we can't change the size. The list is permanently fixed. On the other hand, we could have a linked list. It's a chain of nodes. You can think structs, or it really could be classes. And one of the big positives about that is that it can be dynamically adjusted for size. We can add them, we can subtract them, and if we don't have to shift things around that we may have to do with the array-based implementation of a list. So let's talk more about that. I said they're a chain of nodes, so what would a node look like? Let's go with the struct motif. So we'd have a node, and we'd have an item. It could be an integer, it could be a string, it could be an object. It doesn't, I'm just using an integer for illustration purposes. And then you have a node pointer, which is a little bit odd. It's a pointer to itself, and it's very typically called a next pointer. And don't forget the semicolon at the end of the struct. Okay? So in a list then, how do we store a list? We store it using a pointer, and it's a special pointer that we call the head pointer. And that points to the first node in the list. So it would be a private data member. You'd have a node head in the private section of your linked list class. Okay, so if we have a head pointer, then what does the following mean? For example, if we have head and it equals to null, what does that mean? It means we have an empty list. Okay, so we could test for that, or we could assign it to null, for example, in our implementation, to say it is an empty list. If the head is null, there is no list, there is no chain of structs, of nodes. Okay, so what if the head is not equal to null, and the head next pointer equals to null? What condition does that mean? Means we have a list of size 1. There's one element and only one element in the list, and that might come into play. You might want to look at it a little bit differently. So what if we want more nodes? Well, we could just say, hey, we have a new node, and then I'm going to break it up into 2 lines here. We could call new, and we just call a new node, and it's going to call the default constructor here. And what would happen as a side tangent? What if we did this after making that call? That's what we would lose track of this memory just allocated. That'd be bad, and it'd be called a memory leak. Okay. So in our linked list class, what would be our public what would be in the public interface? Our public methods. You could very much expect to have an is empty method to determine is it empty. You're going to need an insert, or a pushback as it's sometimes referred to as, to insert nodes into the list. Well, if you're going to insert, you probably want to remove. I like to use the term obliterate. And another method is you might want to locate, find, or retrieve. They have slightly different meanings. A node. You might want to be able to get the length or the size of the list and keep track of that. Maybe, maybe not, so we'll put a question mark there. That one's more optional. And in the private section, you'd want to keep, as mentioned earlier, a head, a data member, and potentially a tail too. And you may or may not want to keep track of the size of the list. And you may also want to keep track there the definition of your struct. Make it private to that class, such that only members of that class can access the struct definition and nobody else. That could be very appropriate. That's a common way to do it. So what would you do in the constructor then, as we're talking about the class? In the constructor, you would initialize the head pointer and the size if you're doing a side. What about the destructor? What would you do? You would delete every node that was allocated. Okay, you just walk down the list and delete them. What about a copy constructor? It needs to be a deep copy, or you're going to run into problems. What if you wanted to pass the linked list to a method? You could just use the head to do that. When you're writing code for a linked list, what I strongly recommend is write code for the general case, then verify that it works for every special case. What do I mean by special cases? Special cases would be empty list. If we have an empty list, that's a special case. If we have a single item in the list, there's only one, we're talking about dealing with the first item, first of many. We'll just leave it at first. The middle item, this is often the general case. And while we're at it, the single item, it often it's usually the same as the first item case. Okay, so we don't always need to consider that, but it depends on how you set up your list and how your algorithm works. You might need to take care of that explicitly. Or we might be dealing with the last item. So, for example, if we're doing insertion, deletion, retrieval, finding, we need to verify that it works on these 5 scenarios. In my code, I list them. I say at the top of each method, for empty list, it's going to work like this. For a single item list, it's going to work like this. The middle item, this, the last item. And I put that right in the notes so I know that I've tackled each case and I've thought through it. Okay, there are some special types of linked lists, which I think it's important to know about. There's the dummy head, or sometimes referred to as sentinel, so we don't have to say dummy head because that is kind of a negative connotation. A dummy head or sentinel node list. And what you do is you add a dummy head node. You just make up a node that has no item storing it. And what it does is it simplifies your code so that for inserting and deletion, you don't have the beginning of a list. You never have an empty list. In terms of the nodes in there, you always have a node in there. It'll greatly simplify your code. Whenever I write a linked list, I go with a dummy head or a sentinel node list. How would you implement this? In the constructor, you would allocate the dummy node. If you're in a traversal, just step over that first one when you get started, and away you go. You never have to consider the condition of it's the very first item in the list. And what it does is it avoids a situation where you need to update the pointer. The head pointer is really what it gets around. Another commonly used list is a doubly linked list. Instead of just having a next pointer, you have both a next and a previous pointer. What this does is it prevents you from having to keep track of one extra temporary pointer, meaning often named a previous pointer. And so you just add a private data member, and every time you insert or delete a node, you just update the previous pointer as well. It has some more overhead, but it can simplify the algorithms. Another type of special type of linked list is a circular linked list, where the last node actually points to the first node. Then the definition of head may change, and it might not necessarily point to the same one. It might be rotating, and it doesn't matter. You also need to prevent against infinite loops when traversing it, but there's some times where that data structure very much fits the needs of what you're trying to do. A permutation of several of these is a sorted linked list, where the items are placed in sorted order. The advantages of this is if you're looking for something, you can stop early, whether if you found it or you have, or more appropriate, it'll be quicker to find it. Sorry, it won't be quicker to find it, but it'll be quicker to know that it's not in the list, is the big advantage with a sorted linked list. A common stumbling block when implementing a linked list is mixing up the difference between memory on the stack and the heap. Memory on the stack is only appropriate for the lifetime of that scope. If you're in a loop, that scope is going to go away and reuse it. When you're creating a node, it needs to be on the heap. The lifetime needs to live beyond just that call, and we just need a pointer to it. And so that's why linked lists are made up of pointers. It needs to be on the heap. If that doesn't make sense, understand that principle before you go to implement a linked list. So in summary, here's some key points. Linked lists are chains of nodes on the heap. They're used pointers, and to insert and delete, we change pointers of neighboring nodes. We have a private data member of a head variable, or tail in some cases. We need to be careful to avoid memory leaks, as if you can imagine a large linked list and allocating, deallocating, there's a lot of potential there for memory leaks. If you want to iterate over the entire list, we use a loop and a temporary pointer. And when you're writing code, make sure you verify that it works for the 5 scenarios, being the empty list, the single item in the list, the first item in the list, middle item, and last item. Make sure it works for each one of those, each method. And you may consider using a dummy head node or a doubly linked list to simplify the logic. Signing off.